Okay. The numbers that form the pattern in Pascal's triangle, and I believe you've seen this in grade 11, can be found by using combinations. The combination n minus r c k minus 1, or n minus 1 choose k minus 1, gives the value for the element in number k in row n of the triangle. For example, the fourth number in the sixth row is 5 choose 3. So even this is row number n equals 0, but the sixth row is 1, 2, 3, 4, 5, 6, and the fourth number is 1, 2, 3, 4, right? So the fourth number in the sixth row is really 5 choose 3, because it's 0, 1, 2, 3. So this is row number n equals 0, this is row number n equals 1, n equals 2, n equals 3, n equals 4, n equals 5, n equals 6. Here, for the first one, r equals 0, r equals 1, etc. 2, 3, 4, 5. Here, r equals 6. So even though this is really, if you count the seventh row, this is the seventh number, to get this value, it's 6 choose 6, which equals 1. So I think you've seen this before, where any item in Pascal's triangle is equal to the sum of the two numbers above it. 1 plus 2 is 3, 6 plus 4 is 10, 10 plus 5 is 15, and so on and so forth. Sometimes we don't want to write all the rows to get to the element we want. Like, what would be the fifth element in the 20th row? We don't want to have to write out Pascal's triangle. We can just use combinations, right? So this is 1, this is 1, 1, this is 1, 2, 1, 1, 3, 3, 1, etc., etc. This is 1, 4, 6, 4, 1. So we don't have to write out Pascal's triangle, we can just use combinations. So as you recall, any element, for example, if it's 1 away from the right hand side and 1 away from the left hand side, they're equal. 6 equals 6. So entries equidistant, which means the same distance from each end, are equal. For example, in row n equals 4, 4 choose 0 equals 4 choose 4, 4 choose 1 equals 4 choose 3. So 4 choose 1 equals 4 choose 3. Any items equidistant from the ends are equal. The formula for this is n choose r equals n choose n minus r. Let's just take a moment to prove that. Prove the formula n choose r equals n choose n minus r. Well, the left side equals n factorial over n minus r factorial, r factorial. Right side equals n factorial over n minus r factorial, n minus n minus r factorial. So that's n factorial over n minus r factorial. N minus n is 0, and minus a negative r is just r factorial. So when we apply the formula, I'll just write the formula here for those of you who might like to remember. We took that formula before. Sorry, that should be choose r. C. N and choose R is that. So I just subbed it in the formula. You can see that these are two equivalent expressions. So therefore, n choose R equals n choose n minus R. Left side equals right side. Okay. So, to what other expression in the form of n choose R is each of the following equal? Well, we can just plug it into the formula. 21 choose 21 minus 8, and that's going to be 21 choose 13. So I think you can even experiment yourselves. You can go, well, what is 21 NCR 8 equals 203,490, right? So I'll just write it down, 203,490. And if I were to plug in 21 NCR 13, that equals 203,490. And N choose A would just be, 9 choose A would just be equal to 9 choose 9 minus A. Returning to our study of Pascal's triangle, we notice that each number in any row can be obtained by adding the numbers to the left and to the right of it in the row above. So we can get it by adding 1 plus 6 is 7, 6 plus 15 is 21, 15 plus 20 is 35, 20 plus 15 is 35, 15 plus 6 is 21, 6 plus 1 is 7, 1 plus 0 is 1. We don't have to have all the previous rows to find the elements in row n equals 7 of Pascal's triangle. We can just use the choosing option. 7 choose 0 equals 1, 7 choose 1 equals 7, 7 choose 2 equals, if you just plugged it in your calculator, 7 NCR2 equals 21, 7 choose 3 should equal 35. 7 NCR3 equals 35. 7 NCR4 equals 35. These two are equidistant from the ends, so they're going to be equal. 7 choose 5. These two are equidistant from the ends of that row. 7 choose 5, 7 NCR5 equals 21, so that one equals that one. 7 choose 6 equals 7, and 7 choose 7 equals 1. So instead of having to know the previous 7 rows of Pascal's triangle to get the 8th row, we can just use our choose button, right? What expression in the form n choose r would we predict to be equal to each of the following? Well, 23 choose 18 plus 23 choose 19. Well, that would be equal to, what do you think? We have to increase our row. That would be the next row, right? That would be 24 choose, and I've memorized it like you always choose the larger of the two. 24 choose 19. And you can check that in your calculator. and we're going to prove this formula on the next page, but any two items in the previous row equals the sum of any two items in the previous row equals the sum, and that item is designated as 65. Choose 30. The generalization of this pattern is known as Pascal's theorem. So n choose r plus n choose r plus 1 is equal to n plus 1 r plus 1. So the larger of the two are, I guess that's equivalent to the r in the r spot. You choose the larger of the two, and then we go to the next row, which is, so we add 1. So let's prove it. It's a little bit more complicated to prove this one. Okay. Whenever we're proving again, remember we separate the left-hand side from the right-hand side. This one's the simplest. I'm going to start with that one, because that way I know what I have to get my left-hand side to equal. So right side equals n plus 1 factorial, right? I'm just subbing it into the combinations formula. N choose r equals n factorial over r factorial n minus r factorial. I'm just subbing it into that formula that we learned previously. So right side equals n plus 1 factorial all over n plus 1 minus r plus 1 factorial and r plus 1 factorial. So we know plus 1 minus 1 is 0, so that's going to be, just write the top first. This is n minus r factorial times r plus 1 factorial. So I've simplified the right-hand side as far as I could go. Now let's work with the left-hand side. That's where the bulk of the work is. Left side equals n factorial. I'm working on this one here, the first term here, all over r factorial, n minus r factorial, plus n factorial over r plus 1 factorial times n minus r plus 1 factorial. I'm just going to simplify this. N factorial. I'm just going to rearrange it a little bit. N minus r factorial, r factorial. I'm going to leave a gap because we're going to have to simplify this, and we're going to have to do some algebraic work with both of these. N factorial over n minus r minus 1 factorial, which is this, times r plus 1 factorial. So I want to compare this denominator to the denominator on my right hand side. We've got the n minus r factorial, and I want to bring it up to r plus 1 factorial. So I'm going to have to multiply this by r plus 1 over r plus 1. I'm just multiplying by 1, so I'm really not changing anything. It's going to look different, but I'm not changing the value. Now, if I compare this one to this denominator to that denominator, I have the r plus 1 factorial, but I need to get this one to n minus r factorial, so I'm just going to multiply by n minus r over n minus r. So this is equal to n factorial times r plus 1 plus n factorial times n minus r all over, well, this is going to equal n minus r factorial times r plus 1 factorial. I've got my common denominator. This will equal n minus r factorial, r plus 1 factorial. So I'm going to factor in the numerator. So I've got the denominator equivalent to the right-hand side denominator. I just have to worry about the top part now. So I'm going to factor out the n factorial, right? I have two rather large terms here. N factorial is a common factor to both. So I'm going to factor out n factorial, and I'm left with r plus 1 plus n minus r all over n minus r factorial r plus 1 factorial. R minus r is 0, so I'm left with n factorial times n plus 1 all over n minus r factorial r plus 1 factorial. N times n plus 1 is n plus 1 factorial over n minus r factorial r plus 1. Okay, because you know n plus 1 times n factorial is just n plus 1 factorial. So left side equals right side. Proved. Yes. May I elaborate on any? Okay. For okay, so where did the n minus r minus 1 go? Okay. Do you agree when I multiply 7 factorial times 8, that equals 8 factorial? Okay, because that's just 8 times 7 times 6. So just as an example. So when I multiply n minus r minus 1 factorial, which is like, say, compared to the 7, and I multiply it by n minus r, isn't this 1 up from that? So that's n minus r factorial. Okay? Was there anything else? So this times this became n minus r factorial. Was there anything else I could elaborate on? Was this one okay? Where r factorial times r plus 1 is just r plus 1 factorial? Right? Can I elaborate on anything else or explain anything better? We're good? Okay. If not, when I turn it off, we can talk about it. Okay? Okay. Now, this question is asking us if we go diagonally down like this, or we could go Georgepolya. How many ways are there to spell George Polya? How many different paths will spell George Polya? Okay, so we're going to use Pascal's triangle to answer that. So starting with G, how many ways are there to get to E from G? Well, there's only one way to get there and one way to get there, right? Now to get this O from E, it has to be diagonal, so I can't go that way, right? I can only go this way. So 1. To get to this O, there's two ways. I could go G-E-O or G-E-O. So 1 plus 1 is 2. I'll put a 2 there. And 1 plus 0 is 1. Do you see how we're getting Pascal's triangle out of here? To get from this O to this R, there's one way. To get to this R, I can go this way or this way. So that's 3. And I can go this way. So there's two ways to get to that O. So there's 2 plus 1 way to get to that R. So that's 3. And that's 1. See how I'm just following Pascal's triangle? So 1 plus 3 ways to get to that G, that's 4. 3 plus 3 equals 6. 3 plus 1 equals 4. 4 plus 6 equals 10. 6 plus 4 equals 10. So there's 10 ways to get to that E and 10 ways to get to that E. To get to this P, that's 20. To get from O to O from P, there's 20 ways. To get to O from P, there's 20. To get from this O to that L, there's 20. To get to this L, there's 20 plus 20 equals 40. And to get to here is 20. To get to this Y, 20 plus 40 is 60. 20 plus 40 is 60. And to get to this A, 60 plus 60 is 120. So there are 120 ways to spell George Polly. Uh-oh. Don't know why I put that there. Let's take a look at the checkerboard example. I hope some of you have played checkers before. You can only move in the white boxes diagonally that way or that way. So this question is asking you how many ways are there to get to the other side. Now you can only land in the white spots because you can only move like this, or you could move like this, right? Or you could move like that. How many ways are there to get to the other side? Well, let's take a look. To get to here, there's only one way. Here there's one way. Here there's one way. Here you can't move down. We're always moving upward toward the other side. To get to here, there's one way. Now to get to here, there's two ways because you could go there or you could go there. To get to there, two ways. But here, there's 2 plus 1 way is 3 ways because you could go 1, 2, 3. To get to here, 3 plus 1 is 4 ways. To get to here, there's 5 ways. So you could go 1, I don't know if I can list, 2, 3, 4, I'm missing one. But take my word for it, I'm not sure. 1, oh yeah, 2, 3, yeah, and then 2 ways to get there. So 5 ways to get there. 5 plus 4 is 9. 4 plus 1 is 5. So we add them up. 5 plus 9 plus 5 equals 19. There's 19 ways to get to the other side. Anything I can elaborate on there or explain better?